I am supposed to stand here. So if I wander off, like indicate with your eyes that I need to move back. There's a mic here that I need to speak into. So I'm Amit Shukla. I recently started with Docker. So I've been with Docker 4 months now. It's kind of a happening company in the Bay Area, at least among enterprise startups. I'm an engineer at heart. I've always been an engineer at heart. I also manage engineers, but I try to stay as close to the technology as I can. Over the years, that has increasingly grown less and less, but I keep trying to fight that tendency. So I manage the storage and orchestration team. So I was hired into Docker to start the storage team, because storage is kind of spread out among multiple different projects, and I'm trying to get them together into one place. And then I also recently inherited the orchestration team. So this is the Swarm team. My background is in data storage systems. So I have worked on something related to data for almost 20 years now. Prior to Docker, I was at Twitter, where I worked on the data stack. So caches, data storage, messaging systems, streaming compute systems, etc. And before that, I was at Microsoft working on database systems. And then before that, I was on Teradata working on database systems again. I love building software to solve real problems. I'm not really attracted to solving like theoretical problems that much. Yeah, so you can follow me. I'm at Amit S. But be aware that you get like an eclectic stream of things that I'm interested in, as opposed to like a Docker PR stream of this is what is interesting for Docker, that's what's interesting for Docker. You just see interesting stuff. That's interesting to me at least. All right. How many of you are using Docker today? Okay. So I will quickly go through the introduction, because there were at least 3 people that I saw who aren't using Docker today. So I think if I don't do the introduction, then the rest of the talk may not be as useful. But I'll do a really quick and brief introduction. And this is a storage-focused talk. There are actually 3 places where storage is used that is interesting in the Docker space. The first one is the Docker Hub, which stores images. I'm not going to talk about that. Right. The second is the Docker engine itself. Right. In some way, you have to store images locally and then run them. Right. So how are they stored and run? I will talk about that. And then the third is volumes, which is applications themselves using storage to do something. I'll talk about that as well. Right. Really briefly on Docker. So Docker is a bunch of open source projects. The most popular of which are Engine, Swarm, Compose, Machine, and Registry. There is also a company behind it. Right? Like Linux itself doesn't have a company behind it, but there's like Red Hat and etc. Right? There's a bunch of other companies. Docker has a company behind it. The company is the one that sort of created Docker and open sourced it. So that's sort of one thing that I've found confusing to people, which is, hey, what is Docker? Is it like this container runtime thing? Like, what's this company? So it's actually both. Right? So Docker, the company, is the shepherd of open source projects and providers of issues. Right? There are also a bunch of commercial products, which I will not talk about. There's the hub, there's the trusted registry. Essentially, the open source projects don't have a bunch of the stuff that most corporations want. Open source developers don't really value doing like as much doing like security work or compliance work, those kind of things. And so those things we are developing on the side as an addition to the open source projects and selling them. Right. So again, really briefly, what are containers? I'm guessing everyone knows what virtual machines are. Right? It's essentially machine level virtualization. So you get the illusion, you give the virtual machine the illusion that it's running on a physical machine, but it's actually being virtualized and run on a virtual machine. Right? So the virtual machine itself will have the whole guest OS. Right? For example, this could be Windows, that could be Linux, and then you have the libraries that are part of the application and the application itself. Right? containers themselves are operating systems level virtualization. So you can't mix and match OSs. So you can't run, for example, a Windows OS on a Linux host OS. You can only run Linux or Windows so to be. But what you do get is they share the OS. And so since they share the OS, the amount of stuff here that takes up memory is much smaller, right? So essentially, you get the host OS. I wish I had a point. You get the host OS, and then you get a Docker engine running on top of it. And then the Docker engine shares as many of the bins and libraries among the different containers as possible. And then the containers are the smallest possible unit that can run on that particular host OS. So for example, on Linux, it's the smallest possible thing that can run. Right? This results in a whole bunch of interesting behaviors. Like the biggest problem I found at Twitter, or one of the big problems I found at Twitter was we would deploy bits into production, and it would turn out that the JVM version that we had on our developer machine was different from the JVM version on a particular production machine. For whatever reason, it was different, right? Someone did something to that machine, and then it wouldn't run, or there would be a GC spiral, or something would happen, right? Then it would be like, okay, look, it works on my machine. Why does it work there, right? It's like a very common problem. So this was sort of intended to solve that particular problem, which is you package it in one place, and then as a unit, it has all its dependencies. So if, for example, JVM was a dependency, it would come packaged with JVM. And then you ship it to any location. You ship it to AWS, DigitalOcean, Azure, your local machine, wherever, and it should run as is. Right? All dependencies are packaged. And and because of how tightly packed these things are, how lightweight they are, and we'll look at some of like an example of how lightweight things can be. You can pack a lot of them. We have seen packing, somewhere between 5 and 30x of VMs, depending on the size of the container itself. You can pack a lot more onto a single machine. Right. So I'm going to do a quick demo, pulling a container image from the registry. Now what I have done is I actually already pulled the images. So I had a bad experience like with the thing hanging. So I have already pulled it. But you kind of see how the whole thing goes. You guys see this? I think I'll have to see it like this.
If I need
yeah. I was just joking with him that this will be my first presentation where I'll be kneeling. So this is it. All right. So what I've done is I've created. Yeah, I think there's some issue with sitting and microphones and things like that. All right, let's try this. Let's try this. That's much better. All right, so what I'm going to do is I'm going to Docker pull a particular image. I'm going to pull Nginx. Nginx is sort of a reverse proxy web server, extremely lightweight. Hopefully it actually succeeds. We'll see. All right, so what would have happened if I didn't have it is it would have pulled the bits from the hub. The hub is, let's see. The hub is this thing. So this is the Nginx in the Docker hub. Think of it as GitHub, but instead of it being for source code, it's for images, right? So you can go to hub.docker.com, search for Nginx, it'll bring you to this page, right? This is the official Nginx binary. If you click this link, it will give you the build file or the Docker file for this particular thing, and you can see how it was constructed, right? So it says it started from Debian pulls Jesse, which is like the base OS. The maintainer is this, and then these are the commands that actually got run to form that particular image, right? Some commands and environment settings, blah blah blah, right? This is what you get. Okay. Let me see. Shell. Okay. What I really need is an autocorrect for demos. There we go. So when I do Docker images, it basically gives me a set of images that I already have. Now the cool thing here is if I pull, we saw that the base for this is Debian:Jesse. So if I pull Debian:Jesse, it should already be there. And this is one thing I'll drill into as to how this actually works and why it works this way, etc. Right? This is just will give you a taste of the whole thing. Right? So it won't actually pull anything. The next time I do Docker images, it should show me both. There you go. There we go. We have both. And the sizes actually sort of indicate sort of the size of that image. But because of how the things are stored, and I'm jumping a little ahead here, because how things are stored, the Debian is the base for Nginx, and so the size of the Nginx binary that got downloaded is actually the difference between these two. So it's about 8 minutes. Right? And I will get into this in much more detail in a couple of minutes, or in 5 minutes or so. Right. Right. So we started. Oh, we didn't start the container. Let's start it. ND. So I'm saying run Nginx, call it my Nginx, run it as a daemon, right? And you do docker ps, and it shows me that Nginx is right? This is like the simplest possible demo that we can get into. Right? Now what I can do is I can see if the web page actually comes up. So if I figure out what the IP address of this thing is, Docker machine, IP, I think I called it demo3, figure out what the IP for demo3 is, copy it, here, and let's see. No. Okay. And this is demo3, I believe. So I did pull it. I just pulled it in advance. So it is demo3, demo3. Never mind, let's keep going. I'll figure out how I this doesn't work. Alright, so now comes the fun part. Let's figure out like how is this thing stored. It's actually pretty cool, I don't know what tricks, but pretty cool functionality that gets used here to enable this whole almost magical experience. So containers come out of three things. Like three sort of foundational technologies lead to containers being available. The first one is control groups, like Linux control groups. Essentially give you isolation between processes, right? In terms of I can allocate certain amount of CPU, certain amount of IOPS, and network bandwidth to certain processes or groups of processes, right? So I can control that group of processes using some configuration. The second one is namespaces. So if I want isolation, I want a process running to think that it is the only one and it owns sort of the bit space, right? It shouldn't see other processes running, like another instance of Nginx running, like my Nginx shouldn't be able to discover that other one, right? So that is namespaces. And the third one is copy on write. So if I actually had to duplicate the storage for each of these images, then I would be using like a lot of storage. And in terms of startup time for these things, it will also be slow because I have to load the whole image each time into memory, right? So what copy on write does is it shares as many of the code pages as possible, leading to basically you check, are these code pages available in memory? So if I run 10 Nginx's, the first one will load the code pages, second one will see that the code pages already are there and just reuse it. Right? And we'll dig more into the copy and write part of it. Right? So now this is storage for the Docker engine itself. Right? So I run a Docker daemon on a particular machine, and when I do Docker pull, it pulls some images from the hub to that particular machine, and then you can run them. Right? So for that Docker daemon, how does the Docker daemon actually store images? And let's look at that. So I said there are a couple of one enabling technology talked about is copy and write. And the second one, which is sort of two sides of the same coin, like another side which enables this, is union file systems. And let's look at each one. So copy and write is a pretty standard paradigm in Unix. For example, fork essentially makes a copy of an existing process and then loads whatever code is needed for the new process, right? So it's basically a single shared copy of the data until such time that it's modified. Without this, containers would take a long time to start because I would have to essentially load the binary into memory, right? And for everything else, we load the binary into memory, so we think of it as a normal thing. But just imagine if you didn't have to hit disk to load things into memory because they were already in memory, you get much faster startup time. So that's what this enables, right? So like containers start up in milliseconds as opposed to seconds. Like VMs take minutes to start, containers take a few milliseconds, few tens of hundreds of milliseconds. They will also take a lot of space. So what the union file system, which is my next slide, does is it doesn't store like duplicates of the data. So if two different images share the same components, they actually share it on disk as well. So it's just a pointer to a particular set of components as opposed to like copy. All right. So what are union file systems? Union file systems basically take a bunch of directories or files and give you like union them together and give you like a view of it as though it was a single file system. And we'll talk about this a little more. And so each branch, these things are called branches for whatever reason, represents a layer in the Docker image. And the next slide will dig more into layers. What the layers give us is, let's say your image is constructed out of 6 or 7 different layers, right? As long as, so best way to explain this. Maybe I'll go to the next slide. I think this will help explain. So here what happens is we have the bootfs as the base layer. I have Debian as the next up layer. And then let's say I add Emacs and Apache on top of that. Now let's say I wanted another image which did Debian Emacs, but instead of Apache it did Nginx. Then I would share the layers with this image until the layers actually bifurcate. Like whatever the common part was, I'd be able to share that. So I would share Debian and Emacs, and then I would essentially have another like a separate layer on top, which was Nginx. So that way I'm sharing storage. Instead of having like a large monolithic thing like a VMDK, it basically breaks it up into smaller chunks and then shares as much of those smaller chunks as possible. And the layers themselves are determined based on the Docker file, right? So when I do apt get something in the Docker file, essentially it adds a layer. Yeah, so and then what happens is the layers that come with the image are all read-only. And then when I start a container, I add a read-write layer on top and run the container. I think this example, the next example will make this clear. So this example, AUFS is one of these union file systems. And what AUFS does is you can think of layers as plates of glass, right? So think of these things as plates of glass, and let's say essentially what each of these is doing is adding files. somewhere in the file system hierarchy, right? In the etc directory, or adding binaries or whatever it is, right? So each layer sort of changes some set of, adds some set of files, or modifies or deletes some set of files. And when you are looking for a particular file, you look from the top writable container, and you look and search for, let's say, etc/foo. So I search for etc/foo in the top layer. If it's not there, I go down to Apache, search etc/foo. Not there. I go to Emacs, search etc/foo. It's there, right? And so if it's read-only, I can just return like a file handle to that etc/foo. If it is read-write, what I need to do is, since the base images are read-only and shared, right, I can't go and change the read-only data. So I copy that etc/foo to the top, make it writable, and return a handle, right? So what this also does is, with my container with etc/foo open for read-write mode, when I open it again, what does it do, right? It searches the first layer first, finds etc/foo, and returns it, right? So this is called copy up, right? And so read-only is basically you just find it in the first plate of class, return it. Read-write is you find it in the first plate of class, copy it up to the top plate, and then return the handle. And
takes care of this layer of copy, right?
So do I need to repeat questions? I'll repeat the questions. I'm not sure if this mic will get your thing. So the question was, who actually does this copying of files up to the read-write layer, etc., right? So that comes from AUFS. So this is actually the implementation details of AUFS. So AUFS is I forget what the A stands for. I think it's like another unified file system or something like that. It sort of takes care of these semantics. The way it implements union file system and copy on write is you construct the file system by adding these layers to it, and then you add a read-write layer on top, and it knows that everything below it is read-only, and so it needs to copy up. If you delete, it needs to add a whiteout file, right? So the whiteout file works the same way, which is, if I'm searching for a etc/foo, I search layer by layer. If I delete it, I add a whiteout file. It's just a file with .wh on the topmost layer. So I find it and say, oh, the file doesn't exist. Right? So it's AUFS that takes care of this. And I'll spend maybe a couple of minutes talking about other such union file systems. Some of them, it's not here, it's a little bit later. For example, Red Hat has this thing called device mapper. That doesn't do it at the file level, that does it at the block level. Right? So it has sort of a different set of performance characteristics, but it gives you essentially the same behavior. Does that answer your question? Is this thing sort of clear? It's sort of the crux of union file system. So the biggest advantages of having this union file system is, for example, here, right? Because I'm sharing those files, the files have the same inode, right? If I'm sharing these files across multiple instances of Nginx or multiple instances of things that use Debian, right? So they have the same inode, which means that in the page cache in memory, essentially it just asks for that particular block on the file, and then it's already there because it's actually shared, right? So it's very efficient in terms of memory usage. And there are algorithms to see whether some data pages are actually the same, and the kernels implement this thing called KSM. That's not needed anymore because it's just by design it works out. So these two together enable Docker containers to start really fast. Right? Most of the time essentially is spent reading stuff from disk, right? Because that memory to disk bandwidth is usually much lower than CPU to memory bandwidth and latency. All right. No, so Docker and AUFS together make it so that that writable layer is added. Now, if you don't write anything to that like if you don't change the image itself, nothing happens. I mean, it doesn't take up space. Right? It's not actually making a copy.
Use the space will be
Sorry?
on the space which gets added, you create the writable branch. It's not mandate.
No. So the writable thing is just a layer which is empty until you start writing. Right? So the writable layer does not take up space unless you write. If you're just reading files, then there's like no
It's
data.
just a pointer to the.
Exactly. Well, if you think of it as plates of glass, there are no pointers as well, right? Because when I'm looking for etsy/foo, I look at each layer one by one, which is one of the problems with AUFS, which is you have lots of layers, then finding a file will keep, looking in each layer. Right? So there are optimization strategies for how do you make AUFS perform well, or how do you build Docker containers so that with AUFS there's good performance.
While deleting, just use it common, right? While deleting.
Yeah, while deleting, when you delete a file, it just adds a whiteout file at the writable layer with no data, right? But when you search for it, you search for that name and it finds the whiteout file and says, oh, this file is actually being whited out, so it doesn't exist anymore. So it'll say file not found. So let's actually look at.
This
Yeah.
helps basically shorting the time of the next container. The first container will take the same time.
The first container will read as much data as it needs to, as many code pages as it needs to. Subsequent containers will be much, much faster.
The common use case is going to be like there's one container that is running on the machine.
One of the more common use cases is you pack lots of containers onto the same machine, right? Not just one container per machine. If you're doing one container per machine, then you're not really efficiently utilizing that machine, unless it's. I guess this goes into the philosophy of containers, right? Like the philosophy of virtual machines is you have large monolithic applications, right? Versus with containers, there's this thing called the microservices architecture, which is breaking your application into small chunks, which you can then scale out instead of scale up, right? Like classical databases are all scaled up, right? You want to scale Oracle or MySQL or SQL Server or DB2, you essentially put more hardware, more CPUs, more memory on one box. And then there is scale out, which is Oracle RAC to some extent does scale out. Right? Most of the scale out systems are focused more on data warehousing than OLTP. But still, the scale out support is less. I think a great example of scale out is web servers, like stateless web servers. Right? You don't like build a huge multi-threaded singleton web server. You sort of say, I'll run multiple web servers. All right, this is the sort of the interesting part. Let's look at where these things actually live. Am I running out of bandwidth? I have enough bandwidth. I'm good. All right, so let's see. Let's go to this one. Let's go to this is demo 1. Let's SSH into demo 1. So let's look at where I talked about all these layers and stuff, right? So where are these things actually stored? Let's go to warlib docker, which is where they're actually stored. This is all internal Docker storage. You create volumes, for example, do they go in here? But the thing we are more interested in is this. Right, so we went to the AUFS directory, let's go into diff. So actually you would think that it would be in layers. Right? But these are actually files, not directories, so that they are the manifest that describes what's in the layer. The actual layers themselves are in diff. Right, so these are the layers. Let's just pick something at random. Right? So for example, this particular layer, there were changes to the etc directory and the temp directory. So let's go to etc and see what changed. So this is the directory that got added, and this is the file that got added, right? Whatever it was, right? So this is how you can basically go into the wanted Docker and see how AUFS actually stores the different layers. Right? The good thing about AUFS is it's all file-based. You can actually explore these layers and see what exactly was added in which layer. Right? Like for example, we could go to another one. So from this, that is much harder to do. There is additional metadata that you can use to construct the graph essentially. Yes. How are we doing for time? All right, let's keep going. All right, so we saw where images live. Now, Docker has this thing, has this sort of philosophy that we want to ship a full solution, but we also want it to be pluggable. In the networking space, we have pluggability. In the actual file system used to store images as well, we have pluggability. So by default, Docker on Ubuntu comes with AUFS. On the Red Hat systems, it comes with device mapper. Now, it's pluggable, so as long as certain APIs get implemented, you can have different solutions for this. And there actually are numerous solutions: AUFS, OverlayFS, device mapper, BDRFS, VFS, ZFS. I think this is the exhaustive list. They all implement image composition, like the union file system and copy on write, but they all have slightly different ports. And we'll look at a couple of them, and we'll probably talk about what's recommended driver. Question. Layers are arranged as a directed acyclic graph. So no cycles. There's cycles and no. So actually, if you explore the code, there actually is like a graph driver and stuff like that.
So it's possible that from a node there will be two ways. So which one, which suppose it has to find a file, so which path does it want? Or it represents the
So it depends on how you layer this thing. So there might be a case where two separate sub-images already exist, and then I can construct an image of those two. Alright, so AUFS is the original driver that .cloud, the precursor company to Docker, used. .cloud was into hosting like a platform as service, they hosted other people's applications. And so they strove for density, because density drove cost down, and AUFS is really good with density. We looked at the memory sharing thing because the inodes were the same for the files. So it scales really well. Now it also has a bunch of problems, which is it's not in the mainline kernel due to a variety of reasons. The most important being that the guys who developed it didn't trickle the changes into the kernel. So when they submitted the large patch to the kernel looked at it and said, look, this is poorly documented, it's too large, can't take the risk. No. Right? What they really like is like smaller patches, well documented, that they can understand and take in, because anything that goes into the kernel, like someone has to look at it, one of the maintainers has to look at it and understand every single line of code, every semicolon that goes in, because if they don't, then disaster will happen, right? Yeah, so it's not the mainline kernel, hence there is that Linux image extra virtual package that gets installed as part of the process, as part of the install process. It's also not well suited for working with large files, like log files and databases, etc. Can anyone guess why? Like, why is AUFS not good for like adding to large log files? Yeah, that's part of it. Yeah, the biggest reason is that let's say I make changes to a log file and commit them back. Once I commit them, they go into a read-only layer. When I restart the container, the write layer gets added on top again. Then I have to copy up that file again. right? So that copy up essentially kills you. If it's a large enough log file, copying a large file kills you. Right? Because once you want to write to it, you want to copy it up. Right? We talked about these panes of glass, and like whenever you want to write something, you have to find where it is, then copy it up to the top so you can actually start writing to it, right? For log files, assuming they keep growing in size, and you commit them back to the image, you have to copy them up the next image time. But there's a workaround, like a very easy and highly recommended solution to that, which is for any large files, you should use volumes rather than commit back to the image. The other challenge is containers with lots of layers. Finding a file may take a long time, right? Because you search each layer one by one. So if you have 100 layers, you're basically you might do 100 searches. Another option is device mapper. So the Union file system is a small part of device mapper. It does a whole bunch of other things like RAID and encryption and snapshots and stuff. It's very different from AUFS. AUFS works at the file level. You can actually go into the directories and see what all the layers are. Device mapper is more like a SAM, so it works at the block level. Because of that, it's more complex. Like from the AUFS, you can understand even conceptually, as I explained it to you, like what happens on a read, what happens on a write, what happens on a delete. Here, it's like all at the block level, right? So you can't actually explore the disk format to figure out what's happening. Yeah. And because it is at the block level, in memory, they don't share pages because they're different blocks, you don't actually share data pages in memory or code pages in memory. And so density is a little bit lower. Because of its complexity, there's some amount of tuning required to get good performance. A couple of recommendations there. So I think the summary here is there is no best storage driver. I had a couple of slides on the other ones, but in the interest of time, I'll skip them. So the recommendation basically comes out to, if you have a high density kind of scenario where you want to pack as much as possible, use AUFS if you're using Ubuntu. If you're using Red Hat or CentOS, use OverlayFS, which is another Union file system that is in the kernel. And don't put big files in the container file system. The most important thing is if you're already running some particular file system in production, try to use that. So you have operational experience with that, and nothing beats operational experience. Questions? So I'm going to move on to volumes next.
Just one question: how much is when you have the container? What's the time taking of the container? Getting first container on the virtual machine as well as getting the other machine. The layer shared. So just the containers. Just the first container take time. Then you should get the full and everything. The second container should be time pass. How I don't know. Second easy.
Yeah, so I think the best illustration of this is at DockerCon EU on the keynote of the first day. In Barcelona, we did the demo of, I think we ran a 1,000 machine cluster on AWS with 50 containers per machine, right? And that thing, the 1,000 machine thing, filled up in, I would say, a couple of minutes, 2-3 minutes, something like that. Because it was like a real-time demo, right? And that sort of gets you a sense for this was 50,000 containers starting up, relatively soon, right? And so there were 1,000 cold starts with 1,000 machines, but then there were 50,000 minus 1,000, 49,000 warm starts.
What happens when you kill a machine? When it shuts down, does it copies the entire layer to the download layers?
No, so what happens is
This is the question. What do you want?
So what happens when you kill a machine?
Kill a machine, kill a container, because there are two questions.
Yeah, I'll try to decipher this, right? So, are you saying that I'm running it on a VirtualBox machine, the machine dies? Or are you saying that I gracefully shut down?
So, there's a container that is running. So, both gracefully shut down and it gets killed.
Okay. So if you stop a container, the container stops, right? So I think there are two separate concepts. Yeah, one second. So there are two separate concepts which are interesting to understand. One is images, and the second is containers. They are actually two different things. So a container is an instantiation of an image with the writable layer, right? But you can't push a container back to the hub. And I can make changes to the image and push the image back to the hub. I can't run an image, I can only run containers, right? So when I stop a container, no, so for example, in this Nginx case, right? Once I ran Nginx as my Nginx, that's a container. If I make changes to Nginx, it's only visible to that my Nginx. If I run another Nginx as my Nginx2, it actually adds another writable layer on top of the base Nginx image that I have, right? So that actually the writable layers are different, right? So now what I can do, if I want to commit the changes back, is there's a docker commit command that will commit the changes that I have made to the writable layer back to create a new image which has my changes as read-only. So then further images can build on top of that, and once I have committed it, I can push that back to the hub. Is that explained? Yeah, no, I can, if I stop the container and I like rm-f it, then my changes are gone, right? But
store that as an image and then again run.
Yes, so you can commit the changes and then you can run the new committed version of the committed image as a container. I can also push that committed image back to hub, and then others can download it with my changes.
Generally, committing to actually it's better to just put it in the docker.
Yeah. So I haven't seen that pattern used much. You can do it, but I haven't seen it used much. If you do want to store stuff, like store in an external volume, which is the next topic. Right? Usually, you want your images to come out as part of a build process rather than as part of running. Right? Any runtime changes, etc., you want to store somewhere so they can be reused independent from the build, because your build will not get these changes. Right? Your build will not see that, oh, this new image has been created with these changes. Build will just say, look, this is my Docker file, I'll take it and I'll slam it down. That's it. Right? So if you want some changes to be read again by the newly built images, then you should store them elsewhere, something that can be mounted in, and then you read the config or whatever.
So that incremental read is possible by plotting something there, so we just have to
I think that brings up our next topic, which is volumes. Right? With your application, how do you store stuff outside of your application and then read it by subsequent runs of containers?
Yeah.
Right?
This is what we're talking about.
Yes. And I'm also looking for your feedback on how you're using it, etc. So, like, keep your feedback coming and stop me at any time.
Just one thing. CentOS default of the developer is device mapper with feedback. It's generally almost always bad.
Yes. So if you do device, actually I skimmed over this a little bit.
We've actually encountered bugs in terms of disk usage.
Yeah.
And there's literally nothing going on. We deleted everything and I don't know what happened inside. Device mapper with loopback is generally not a very.
Yeah. So device mapper should not. So device mapper by default, if you say storage opt equal to device mapper when starting Docker, it does loop back. So it stores the device mapper metadata and data files like on disk, as opposed to a raw disk, right? This is sort of called the loopback connection. That has bad performance and should not be used in production. I think it's good for dev environments or acceptable for dev environments, but not in production. In production, you should actually map it to a raw disk. But I think the caveat applies, which is there is no perfect solution here. I think the high order bit should be, if you have experience in production with something, try to use that. And if that doesn't work out, then all right. Should we move on? Okay. So now the rest of my talk is going to be more demo than talking. So what are volumes? So a directory mounted inside my container that exists outside of the Union file system. Now I'll do a few demos where it does exist inside the Union file system, but it could exist anywhere. I just did create an NFS share and mount it in there. The demos will all have it inside, but it's actually meant for outside. And the directory lifetime is then independent of the container lifetime, right? And that solves your problem. Right? If I want to make some changes, then I want future builds of my container to use it, this is the perfect system. Now you can mount these volumes either via Dockerfile or via command line interface. You can sort of two interesting cases. The more common case I expect will be mount to a remote storage device. There's one particular interesting use case which is mount an existing directory on the host into the container. And the coolest example of that is if you develop for the Docker Engine project, the default build system is in a container, right? So you git clone and pull the Docker code base. You don't have to install anything to compile the code base, right? You just have a Docker container which has all the binaries necessary to compile your code base. You run the Docker container, mount your repo as a directory into it, and then you can build just via Docker commands. Right? So I think that's the canonical example of why you want to mount directories on your host into a container. Other than that, it's generally a bad idea because you want containers to be portable, and once you tie it to a particular host by saying that, like, look, there's this directory and I want to mount it in here, then you're kind of tied to that host. Okay. Yeah, so as I said, almost always recommended to use a volume. It is almost always faster to write outside the Union file system. There's a link with a perf study in there where they essentially have like 2x or 1.8x increase in performance and IOPS and throughput by like storing things outside of the Union file system, like local. I think this was a local directory. Yeah. All right. Let's look at this. Seems to be a party with there's music coming. It's good. I heard there's beer next door. We're gonna go there after this. All right. Back to the MacBook. Docker run as a daemon. The -v is for a volume. I'm going to mount /www -p. I'm going to run Nginx, so I'm just going to do some port mapping. Alright, so let's run this, and then it's basically running this. Now there's where did that directory go? /www, right? So let's inspect the container. There's a whole bunch of stuff here, and let's search for volumes or mounts. Here we go. Right. This is the stuff we mounted, and our stuff went in here. Right. So that's where the /data file went. And in a minute, we'll look at like dropping a file in there and seeing. So when I did that /www, it actually went into the Union file system. I didn't map it to an external volume. But this is where it sort of got mounted inside the container. Right? And I can do the same. I can either do this or I can do the same with just in the Docker file. I can do from Nginx and just add a volume, and this will be my new container, which also maps a volume. Right. So we found a volume located in the container. Let's add a file to it. Here we go. This is kind of a cool trick. I do docker exec, there's IT. So I exec, get an interactive terminal, and I go to my nginx 2, and I run /bin/bash. Okay, so now I'm actually in my nginx 2 container. So I can go to /w, and this is the directory that I mounted. Okay, so let's touch text, right? So it's there. Let's exit the so just so I'm clear, I actually ran bash in the my nginx 2 container, not on the host where I was running, but inside the container itself. Okay, so inside the container, because I mounted /www, I was able to go there. When I next I'll SSH into the host where there is no /www, we'll figure out from this docker inspect where the thing is, and we'll see the file there. Okay. And let me just copy that thing. What I want. That's not what I want. Two. I think. Okay. cd var lib docker volume. See. Demo 1, that's why I did that. There you go, put text. So this was like, so in the earlier one, what I'd done is I had SSH into the container itself. I had added like a touch foo.text, and I exited that. And now I have SSH into the machine where the container is running. And on that machine, this is the path where that particular volume /www was mounted, right? So essentially what I've shown is the thing exists, right?
So you're directly accessing the file.
Yes, yes. So if I, edit the file and add some text, it will show up in that menu.
Use as common launcher.
Yes, yes, all questions.
How does permissions, how do permissions, create a file in the container? The owners, the group, and the file permission. If I edit it outside the container, how does it affect the container?
It's all root, unfortunately. So the security part we are working on. In this case, it is root on the machine, it's root on the container. There's a feature called user namespaces coming, where I think it's experimental now. I'm not sure if it will ship at 110. 110 is shipping next month. Like the user namespaces will make it so that root on the container is not the same as root on the machine. Right now, those two are the same. User namespaces will fix that, and then we should be in a better state.
The experimental flag.
Yes, user namespace is an experimental.
Yes,
So what's the question?
No, I was saying that thing can be done with the experimental flag on it. You can still check it out with the.
I mean, you can check it out, but not yet in production because the bugs are still being ironed out. But you should check it out because then if there are bugs, you can report them and work with them. Contribute to open source. There you go. All right, so we did this project. So we talked about mounting a host directory on the container. Like the source code and build scenario was what we talked about. It's not portable, so you should use it for specific situations. Then data-only containers was a pattern that was recommended until 1.9, which was November, I believe. Before that, it was like if you wanted to use external volumes, you use data-only containers. So the container basically mounted a volume and then exited, and that volume would be accessible to all other containers running on that machine. I think now we're officially recommending you don't use that because of this thing that we shipped in 1.9, which is named volume support. So volumes are now Docker engine level concept. You can do Docker volume create, Docker volume inspect, Docker volume ls, and Docker volume rm to manage volumes. So let's actually do this. Right? Let's do this 1.9 plus only. Let's create a volume, inspect the container to find the mount point. We'll run a script in the container, and then we'll see how it evolves. Okay?
So here shown that was previous version.
Yes, so you can do that, but this is sort of the recommended way of doing it. This is production ready, etc. This is not a experimental thing. Okay. All right. So demo 1. So Docker volume create. What did I miss? Name. There you go. Volume ls. These are my volumes. One of them is my volume 2. The fourth one from the top. We'll talk about this driver thing. Right now they're all local. We'll talk about what a non-local driver means in a couple of minutes. And I promise I'm getting to the end of my presentation, so let's see, Docker volume inspect. There we go. So the name is my volume 2, driver is local, mount point is listed there, and let's now have some fun. Docker. I'll just try to run a small script as a daemon with a volume, my volume 2, which I just created, mounted to /data inside the container, and I'll run this image called busybox, which is just a lightweight image with a few tools. I'll run sh-c echo hello to /data/file.txt. Something. That's it. Right? So this thing actually should have run and completed because it was just doing that echo hello ps -a. There you go. Which was it? It was 739. So it was this one, right? It exited 8 seconds ago. The names are awesome, right? Desperate Hopper, Admiring Darwin, Cranky Austin. All right, so that thing is running. Let's SSH into the machine and demo 1. Before that, what I want to do, Docker volume inspect. Then I want to know this path. We can go look at it one last time. Okay. Docker machine SSH demo 1. Right, so there's the file. Okay. Right, so we wrote hello, and let's run another one, write world, just for the fun of it. Okay, so we've created that volume independent of a container's lifetime, right? It ran, one of them added hello, this one should add world, right? And let's do another one to just cat it out. So we want to see the results, so let's run it not as a daemon, just as interactive, and let's do cat data file.txt. I should say hello world. Right? So it's essentially illustrating that the volume is now independent of the container's lifetime itself. Right? So what you would have achieved with data-only containers, now you can achieve sort of more interestingly with top-level volume command. All right, last couple of slides here. So the demos I did were all storing files in the Union file system, right? But that's sort of not the recommended way, as I said. And what you really want to do is store the stuff in other storage patterns. So we are working with the different storage vendors to write these volume plugins, which enables Docker to essentially mount those volumes into a Docker container, and then you can write to those volumes. And then those volumes are independent of Docker's lifetime completely. Right? They're managed separately, like they could be a NFS device somewhere. So then they're independently managed, you can write to it. That's sort of how you take care of the stateful part of your application, managed separately from the stateless part of your application. Sorry?
Plugin data.
What do you mean by plugin play?
Using the storage, EMC and Zipper, these are the people who are tying up, right?
Yes. So you can write your own, so plug for writing your own. We're partnering with the various NFS and SAN vendors to start writing these plugins so that then you can mount them in using this storage option into your Docker containers. Okay, question? So, Kubernetes does. I don't think we have a clusterfs driver yet. No, they aren't using the volume driver support that we have. I think they've implemented their own, like as a separate layer.
I understand Google is actually the content space for modern tenants. Actually, in 2006, 2007, you make Google search in the bar, there's a container getting spawned to it in their data center. So they are long time players. So Kubernetes is
Yeah. No, so like Linux containers as such have existed since 2006, right? I think the key breakthrough that Docker has made, actually it's less of a Docker has sort of made this breakthrough. It's like technology has evolved to a point.
It actually came with cloud and all. Informed in niche. This cloud company is coming out, it just exploded. It's the perfect fit. Containers, I need to work, I need to scale really fast. I can't do like what we had baker and BN2.
Yeah.
You start a baker, I will put a coffee, have my breakfast and come, and then it will totally come online. So that's where it really.
Yeah, I think it's a confluence of technology evolving to a point where it can be reused for in a more general purpose way here. Like at Twitter, we used containers, but not Docker, right? Because it pre-existed Docker itself. But we didn't. It was sort of a completely managed environment, so we didn't care about process isolation. Like the namespaces support, we didn't care about. Right? What we cared about was CPU and memory governance. So we said, okay, this thing gets so much CPU, that thing gets that much memory, and we know that we have all the source code, all the developers work for the company, like all the developers work for the company. So that level of trust is there, and so they won't mess each other up, right? When you're outside of a corporation doing this, then you can't have this level of trust, and then you're sort of more in the defensive mode, which is like, let me isolate these things, or even the compliance, right? For compliance, you need to make sure that no one can mess with something else. So I think the technology also has evolved to that point where this is enabled. I think user namespace, like not user namespace, but namespace support, like the PID isolation, came fairly recently. I think LXC has also been evolving. I think the final piece of this containers puzzle was the copy and write file system, right, which made starting them much more efficient than without a union file system. So it's kind of, it's like the, like in 2000, etc., there were all these companies which were doing grocery delivery and stuff like that, and they all failed. But then now Amazon is doing that thing again, at least in the US, and maybe it'll succeed this time. Like, we don't know. So it is the technology ready for that particular point in time or not? Right? I think there's some part of that as well. All right. So in summary, we did a quick overview of Docker. If you need sort of a more detailed overview of Docker, chat with me and I'll point you to a bunch of talks. There's tons of good material on this. I wanted to sort of talk more about storage, since that's close to my heart. So we talked about image storage, maybe not at the level of depth we could have, but I think at a sufficient level of depth for a broad enough audience. We'll talk a little bit about volume. Questions?
About storage, I just glass all apart, right? So how does it do? So where does volume come from? Like, in the right, does it just write the pointer over there, or what is it?
No, so the volume gets added at the topmost writable layer. Because you're now changing the contents of the thing, right? The only thing you can change is the topmost layer. So the volumes get added to the topmost.
So only like slash right? So it's like slash data to that volume. It's a pointer over there, or it's a layer over it?
It's in the topmost layer.
Okay, so the rightmost layer is not a topmost layer. Now the volume layer is a topmost layer.
No, there's only one topmost layer, it's the writable layer. Yeah. The volume gets added to that. Remember, each layer is just a bunch of files and directories. Right? So you just add one more directory to the topmost layer. Right? If there already was that directory, shouldn't be in the stack below it, then you would copy it over and add new files to it.
So if there are 2-3 containers, then every container will have that same volume data, right? Because everybody is telling the same volume.
Yes. So each one would have its own writable layer.
If I put the changes in SH into it and change the file, then everybody, every container looking into it, the file will change.
So now you're getting into this one thing called volumes from. So there's this flag that you can provide to Docker engine when running a container called volumes from, and that tells you, you get this volume from that container. Right? So that's how you read the things written by another container. Otherwise, each container has its own independent. Like if I ran 5 different nginx's with /www or /data, they would write different things, and they wouldn't know about each other unless you said, okay, read it from there.
But with the name volumes, it won't change.
Yeah, so named volumes is different. Named volumes is the Docker engine level volume definition. You can, so I think this evolution hasn't been sort of the cleanest evolution. We started with volumes at the container level, only at the container level. Now we've introduced volumes at the Docker engine machine level, right? And so, but we haven't taken away the volumes of the container level. So they both exist. So I think there's to sort of use it carefully so that you know which one you want to use.
Name volumes are the machine level, right?
Yeah. Named volumes are the machine level. You can have container level volumes as well, but then you get into this finicky, I need to use volume from that container and so on, right? And I think volumes from is also slightly dangerous because what if these things got rescheduled and they're not running on the same machine anymore? Because volumes from works only if both containers on the same machine, right? So that portability thing, I think the cleanest sort of expression of that portability is at the Docker engine level. You make sure that you mount the volumes you want, and then when you schedule a container, this is all not yet implemented functionality. We get into?
Right now it is all good. If you get into the user groups,
Yeah.
complexity will increase more.
Yes. You will have to say, you will have to grant access to certain set of users. Yes, all that will have to do. But I think this part of the stack is evolving fairly rapidly. I mean, this part is evolving, the other part evolving rapidly is orchestration. These parts of the stack are less mature than other parts of the stack. They're sort of rapidly evolving.
Good time for that. feed the guy under that comes from London, right? The south of the school. But yeah, Kubernetes is like at least 5 years pedigree coming into this. So they've got the experience.
Yeah, the problem I've noticed with Kubernetes is it is very opinionated, and that adds to a lot of complexity to the system. So it's almost like you need a master's degree to get started with Kubernetes, because it's like there are so many concepts of pods and application controllers and services, and then each of the volumes is like a separate concept as opposed to being like a plugin, right? I wish they had simplified those things so that it was more approachable. But I know where they're coming from. They're basically looking at Google Borg and saying, look, it has all these bells and whistles that have evolved over 10 years. Of course, we need everything in one shot. But when Google Borg started, it started off with a simple system and then evolved into a more complicated system, right? I think that's the difference.
How do you think so? What should do? Like, suppose I'm demos on engine. That's very simple. Let's put a little more complex. Engine X plus Redis. I gotta make sure Redis is up. There is only engine. So, okay, Redis ready. So that linking, that what we have, that's linking. How we always do that?
That's what we said. We not put orchestration in this.
Okay.
We have our host for system checking and we can
so not the linking is still not happening. You don't check it out. Because with the Kubernetes, the pods, you can always say these pods need to be up.
Yeah.
Then these pods sequence ratio, otherwise you don't up them up. So these things that they have ready it's complex, it's not a simple thing. A lot of it's like being in a aircraft cabin, a lot of buttons.
Yeah.
Just to start, if you're like a novice, you don't know what press anything, just press everything to go on.
No, so
Kubernetes is an organization.
Kubernetes, if you use Kubernetes out of the box, you get all these features.
it's like they have, you can see why each piece of complexity sort of exists and what the use cases, etc. So I'm not saying that it's complex for the sake of being complex. It's complex because the problem space is complex, but it's not super approachable, right? So the thing is, can they simplify it down so that it's approachable, and then when you want more functionality, you add on the layers. Oh, these are the pizza boxes to elevate the thing.
And with the heat of your laptop, you think of warm.
So the joke is that earlier there was this table, which is this high. And I was joking that this might be my first presentation while we're kneeling and presenting. And he is like, oh, there's Domino's pizza boxes, let's stack them up, and then of course they're small.
Any questions? Any more questions? Anybody on that?
Yeah, there are questions.
One question regarding Storm. So we move towards orchestration. So what would be good? Having a small image size or anything would be fine. Reducing the image size is necessary or not?
So I think in general you want images to be small, right? Otherwise, if you're saying that you can make the image smaller but you're not, then essentially you have needless CRUD in that image, right? And that CRUD might create security vulnerabilities, whatever it is. So you want things to be as lean and mean as possible. Right? So I think that thing applies regardless of Kubernetes or Mesos or Swarm or whatever it is.
So if you deploy multiple applications on one server, the idea is to utilize the capacity or the power of the machine using multiple containers. How do you actually make your application? Do you make an OS level dependencies as part of one container? And then run all the applications in separate containers on that machine? How do you actually implement that kind of solution?
No, I didn't understand your question.
For example, you have 4 to 5 web applications, and those are not much larger scale applications based to scale out to multiple machines. I have a big machine, right? I want to run all those 5 applications on this one. Now there's an OS level dependency which the machine, for example, Nginx is T-shirt is an application. It needs to be Redis, some application using Mongo as well. So shall I build a container which will have Nginx, Mongo, Redis, and then a container for each of my web application? Or should it be part of each container? It should have the images of Mongo, Redis.
I mean, the simplest way to think of it operationally, right? When something changes, you want to change the fewest number of running things as possible. Right? That argues for having as lightweight a container as possible. Like for example, if you patch MongoDB, you don't really want to go redeploy your Nginx, right? So you want to keep them as tight as possible, so that when you patch MongoDB, you only restart the MongoDB containers. That said, what you want to do is share everything below that as much as possible. So use the same Debian image or Ubuntu image or Red Hat image or whatever it is. Then as much as possible, order them so that they are the same stack and then change. That makes sense? Sorry? I think it. Sorry? Yeah.
Is the non-veg pizza also?
It depends on your environment, right? Let's say you have you're using CentOS. If I say you should use Red Hat, you're like, look, I'm standardized on CentOS, right? Or if you're using Ubuntu and then I say you should use Red Hat, then it's right. I think in general, for the thing we've seen run well is Ubuntu and CentOS. Those are the two things that we are fairly comfortable with. But again, it depends on what support contracts, etc. that you have. So as long as you have a modern Linux kernel, which I think is like 2008 and up released, it's like 2.4 or 2.6, and right now we're at 3.2 or 3.3 or something like that. Agnostic. I think it depends. It's like an optimal question.
Because we have
Yeah. So you know how to deploy and patch CentOS. Stick with CentOS. I think that's a simple answer. If you're not happy with CentOS and exploring something else, then do the operational exploration first before saying, okay, Docker. I mean, Docker is kind of agnostic, right? So don't do things because Docker says you should do things. Do things because they work for you. And that's why the whole pluggability thing also is there. Because look, there's a way to do it, but then there's also extensibility points. Like with our networking stuff, you can plug in D or Cisco or like whatever it is. Whatever works for you, like that's how you should make it.
So for every Docker commit, we had one more layer. So is it like, can I say that, okay, I want to remove all the previous commits and this is my final Docker file? So that I can reduce the layers.
Yeah, you can, but that's just constructing a new image. Right? If you're constructing a new Docker file, that's just a new image. So in the Docker file also, each line that changes the file system adds a layer.
Yes.
What you can do is you can do this ampersand thing and construct a long string of things, and then take only one layer instead of 3 layers.
So I think we've seen in Docker files. Are you using copy add? Using a lot of copy add. Usually recommended don't use copy add. Use the wget. Yeah. Untar everything and then remove everything off. Code is not required. Only the file is. So it's more smaller. Basically C plus alloc deallocate kind of memory actually.
Yeah. But then there's also the too much optimization, where if somebody in the future reads that thing and doesn't understand what's happening and sort of screws it up somehow, I think that is worse than anything else, right? So you write code that is readable because it's read more than it's written. I think everything should be that way. Like you write Docker files with the intention that someone who is not you is going to maintain it at some point, and they should be able to understand easily what it's doing.
Also, the sharing point still matters, right? The number of layers. So later also matters in sharing.
Yeah.
Yes.
Essentially, you should design such that you can do
As much as
best
possible.
utilization process.
Yes. You do Debian, and then there's like a bunch of packages that you use in all the things. Put them all together, and like here's your new base, and then you can do from your new base so that everyone uses that. Rather than everyone following the same sort of commands in the Docker file, you create a new image with your base thing, and you say from my new base, and then you add new stuff.
You're using anything like proper Docker cluster registry? Okay, I'm here speaking with I'm hopefully not on the hub somewhere. You have a Docker cluster registry kind of thing? Yes.
You have a private registry.
But is implemented using proper cluster registry or like your own?
Docker registry.
Cluster registry.
Now you guys must be just using the registry, right? The open source registry.
We started with one node, but now we are.
Yeah, I think that's the one place where we are seeing, but it makes total sense to do it. Like there's no caveats about you shouldn't do this or whatever. Basically, the thing is that the hub is for most people far away in terms of network distance, right? Even in the US, right? We sort of have, I think, 2 or 3 different Amazon geo regions. But even there, it's far enough away because when I want to pull images onto 1,000 machines, and I keep going to the hub and fetching, I'd rather have my thing local in my network so that I can like quickly fetch those images.
So in Indian scenario, that's a no-brainer.
Yeah. I mean, I'm pulling here and I'm like, look, I can't do a demo with a pull because it takes too long, right? But we are working on it in another angle where we're looking at it saying, what if we were to implement a Tor-based, like a torrent-based distribution system for images within a cluster, right? Usually you're not going to run one Nginx, you're going to run a few Nginxs. So as long as you fetch once into a cluster, then can you distribute within the cluster itself, right? And a cluster is usually closer to each other, maybe with the same top of the rack switch or whatever, than any local registry you would run in, right? That might be a few Tor switches away. This one is probably like one top of the rack switch or the next adjacent rack or whatever it is, right?
You have an agent on one of the nodes.
We already have an agent, right? Docker engine, right? So the thing is, it's a super interesting space. Like how do we get image distribution within a cluster to be as fast as possible? Right? And there are faster mechanisms than single threaded pull, right? Which is what we have today. Actually, we have multi-threaded pull of the different layers, but still, each layer gets pulled as one stream. Right? You can't get, let's say, 10 nodes in your cluster already have that particular layer. You can't chop it up into bits and fetch different bits and panels from different nodes in the cluster. But those are the kind of things that we are exploring.
I have a not storage related question, but this is a generic thing actually. Can you think of some options? Can you give me options when you start Docker, which are generally you see having very bad downsides, specifically production?
I think doing loopback on device mapper is definitely one.
Yeah, stuff like that. Basically.
Yeah, I think that's definitely one. Other than that, I haven't heard of serious ones, but I suspect that is more due to my lack of knowledge of the scenarios than there not being other serious
so there's
things to
one
avoid.
I encountered recently which I didn't understand. So basically, Docker native, the zip container, it allows your C groups to be either systemd or C group ls. So I try to understand what the difference is, and probably the documentation is sort of lacking there when I didn't understand the difference.
Send me a question.
If I put that and it starts working, that's something.
No, send me a question. I'll find the dev who's working on this, and I'll get you the answer. So there's a guy who understands this through and through. A guy called Michael Crosby.
I'll follow it up there because there's this random issue we were facing where it was crashing, like the container crashes. There's this thing, it's only on Red Hat CentOS 7. And so basically the solution was you put this and it starts working. And it does start working.
Interesting. Is there like a web search which says go do this?
It goes to a GitHub issue, Docker issue.
I see. And the Docker issue has a thing saying do this, it work.
Yeah.
Okay. Interesting. Other questions? Was this a useful?
Yes.
knowledgeable.
I have used data only containers till now and I'm facing problems with that.
Yes.
So our company sort of like gave up on Docker and they told don't use it because data only containers take a lot of time to fetch.
Yes.
So they're sort of giving up on it. So I think I will go on to volumes.
Sounds good. Yeah, I didn't put my email address up there, but it's amit.shukla@docker.com.
Yeah,
Send me mail.
Coordinates, put it on the
Perfect.
put on the mail actually.
Just send me mail. Feedback. This thing is busted. What should I do in this case? In some cases I'll have answers. In some cases I won't have answers, but I'll know who to ask. So I'll ask. Who?
Okay. Done? Okay, no question? Okay, thanks a lot, Amit.
Thank you.
And for all your trouble, we have got pizza for you. One few things, just last few questions.